I'm Soumya Bhattacharya, and today I'm going to talk about a very specific and powerful feature in Dart that lets you write clean and professional code. Have you ever looked at a standard library class and thought, I really wish that it had just one more specific function? Today, I'm going to show you how you can add it yourself. So, before we proceed, let us first look into a roadmap. First, we'll define the locked door problem, the frustration that led to the invention of extensions. Second, we'll introduce Dart extensions as the structural solution to this problem. Third, we'll analyze the syntax required to implement extensions, including type resolution and scope. And fourth, we'll review real-world implementations for string manipulation and discuss how this simplifies the development lifecycle. In standard object-oriented programming, we usually treat a class like this solid, immutable building you see on the screen. It has its foundation, its walls, and its residents, which are the functions and methods defined by the original author. Now, here is a problem we face in modern development, especially when you're working on something complex. You're almost never the architect of the building. You're using the Flutter SDK or the Dart core libraries. Those buildings are already finished. The concrete is dry. You cannot just walk in and add a new room because you don't own the blueprints. This is exactly where extensions come in. Now look at the right side of the graphic on the screen. Extensions allows you to build an annex onto the existing structure. We are attaching new functionality to the outside of the class. Crucially, while it looks like it's part of the building to the outside world, it respects the internal privacy of the class. This enforces the open-close principle. The original code remains closed for modification so that we don't break it, but is also open for extension so that we can use it. You are extending the capability without altering the source integrity. Now let us talk about the locked door problem. Imagine you're using a library widget or a standard data type. You need to do something specific, maybe format a date for a specific time zone or calculate a vector for your display. You go to add the function and you hit a wall. The source code is read-only. It lives in your package cache. Before Dart 2.7, how did we handle this? We used helper classes. You would create a file like stringutils.dart and write a static method like stringutils.process. Inside, you can write my text. This is technically functional, but architecturally it is messy. You have to stop your logical flow to find the helper file. And the second problem that it faces is readability. It reverses the natural subject verb order. Instead of data process of self, we are saying processor process this data. We want to eliminate that friction. We want to unlock the door without breaking the lock. So the question arises, how do we implement this? Now, it is deceptively simple, but there is a lot happening under the hood. You need to know two keywords, extension and on, and the formula is extension name on type. The name gives you extension a name, like string extensions. This is critical for scope resolution. If you and another library both define an extension called capitalize, the Dart compiler uses this name to resolve the conflict. It prevents namespace pollution. And next is the type. This is your target. You are specifying exactly which class you are upgrading. Now, static resolution here is the most important technical detail. Extensions are resolved statically. This means that Dart compiler figures out exactly which method to call at compile time, not at runtime. It essentially rewrites your code behind the scenes. This is why extensions are performant. There is no visual table lookup or runtime overhead. It's as fast as calling a static function because technically that is exactly what it is. Now, let's look at some code. We are defining string extensions on string. We want to add a capitalize function which Dart is missing by default. The this keyword mechanism here is that in normal class, this refers to the instance you're coding in. In an extension, this refers to the instance of the object you're calling the method on. You have access to all the public properties of that string. So what we are doing in this code is that we writing an extension which is string extensions on string. Inside, we write a function that takes the first letter which is marked by this of index 0, make it uppercase and add the rest of the substring to it. Now looking at the main function at the bottom, instead of writing capitalize name, we can now simply write name.capitalize. It looks like it was the part of the string class all along. You can also see that we can apply extensions to numbers as well. Here we have an extension mathx on int class. We define a method doubleIt which simply doubles the this instance into 2. This allows to create domain-specific languages. You might need to handle physical units like degree, method, seconds. Instead of writing conversion to meters, say a value 10, you could write simply an extension that lets you type 10 dot meters. You're effectively turning raw numbers into small objects that understand your project's specific context. It makes code incredibly expressive. In large-scale projects, the bottleneck is rarely writing code. The bottleneck here is reading and finding code. Think about the old helper class pattern we discussed earlier. If I write a personalized algorithm in a class and you are a new developer on the team, how do you know that this class exists? You don't, right? You have to read the documentation or grab the code base or ask someone. The API is hidden. This creates high cognitive load. You have to keep a mental map of all the utility classes in the project. If you forget one, you might rewrite code that already exists, leading to technical debt. Now look at the menu on the slide. When we talk about custom functions appearing in autocomplete dot menu, we are relying on a specific piece of technology that is the Dart analysis server. This is an engine running behind the VS Code or Android Studio. Here is a technically what happens when you type that dot. The analysis server looks at the variable on the left side of the dot. It determines its static type. It knows specifically this variable is of type string. It then queries its index of all the symbols available in your current scope. It looks for native methods, but it also scans for any extensions on string that you have imported. It merges these into two lists. To the IDE, your extension method, summon unicorn, is treated as a first-class citizen, identical to a native method like substring or length. Now you ask, why is this critical? This shifts the burden of memory from the human to the machine. You don't need to remember where the function lives. You only need to know what object you're holding. If you're holding a string, the ID tells you everything you can do with it. This is more powerful than writing a helper class. The slide also mentions a more natural readable code flow that reads left to right. In computer science, we call this a fluent interface. Without extensions, complex operations often look like function nesting or onion architecture. Technically, the computer executes this from inside out. For example, if we have a function like save to database, inside it we have a function serialize, and inside that we have a function which is capitalized on a string object named name. It works in an inside out manner, like first capitalize is performed, then serialize is performed, and then save to database is performed. But humans read from left to right. This code forces you to read strictly from right to left to follow the data. With extensions, we flatten this hierarchy into a linear chain. where we can write name.capitalize.serialize.save to database. This reduces the cyclomatic complexity in your mental model. You are following the data transformation pipeline linearly. State A becomes state B, which then becomes state C. This is why we say extensions simplify your daily coding practices. We aren't just saving keystrokes, we are aligning the code syntax with the logical data flow. Let us also talk about a benefit of easy to discover. The Dart analysis server can only show you extensions that are in scope. If you define extensions, say my extension on string in a file, say file a.dart, and you're working in file b.dart, that menu will not show your extension unless you explicitly import file a.dart. The conflict issue is that what happens if two different files both define, let's say, a function summon unicorn on string? The IDE will detect a symbol conflict. It might hide both, or it might force you to use the extension name as a prefix wrapper. Say my extension variable dot summon unicorn. This is why naming your extensions is actually a technical requirement for disambiguity, not just a stylistic choice. Now let us talk about the limitations of extensions. I want you to stick to the dog analogy on the screen. Think of a class instance and object as a living, breathing dog. We have methods such as tricks that we teach our dog, such as sit, bark, shake hand. These are all behaviors. And the fields, which are the variables that are the body parts, which is legs, tail, ears. This is a structure. Extensions allow you to teach the dog new tricks, which is methods. Extensions do not allow you to give the dog a fifth leg, which are instance variables. Why? Because teaching a trick is just adding a new instruction to the brain, that is the code. But adding a leg requires changing the biological structure, that is the memory layout of the animal, which you cannot do when the dog was born. Now, extensions cannot provide extra memory. Let us talk about a low level computer science reason for this. When you define a class in Dart like class user having attributes like name and age, the compiler calculates exactly how much memory a user object needs. Let's simplify and say that it needs 16 bytes. When you run your app and say new user, the virtual machine goes to the RAM and allocates exactly 16 bytes for that object. That space is reserved and it is fixed. Now, when you define a new extension, say user extension on the object user and try to store an extra data such as username, you're asking the 16-byte object to suddenly hold 24 bytes of data, but the object has already been created. The memory has already been allocated. The virtual machine cannot just inflate the object in place without overwriting the memory next to it. This is why we say that extensions can only help you to add behavior, which is the methods, and not add extra memory to the original class. Now we can also just say that can we not use getters and setters? So to summarize, use extensions to unlock classes you cannot modify. Use them to make your code read like a sentence, but remember they are only for behavior and not state. If you find yourself needing to store a lot of new data on a string or an int, you should probably not be using extensions. You should write a wrapper class or a new model. Do not try to mutate the fundamental structure of the objects you are borrowing. That is all with the presentation.
So starting with the string extension, let me first explain the first getter called the capitalized. This getter returns a string with its first letter converted to uppercase. As you can see, I have used the function to uppercase here. The implementation is simple. First, I check if the string is empty using the isEmpty property. If the string is empty, I return the string as it is because there's nothing to capitalize. If the string is not empty, I use the string interpolation to combine two parts. The first part is the 0th index to uppercase, which gets the first character, converts it to uppercase, And the second part is the substring itself, which gets all the remaining characters starting from index 1. So if you have a string like hello, the first part gives you capital H, and the second part gives the rest of the substring starting from E to O. This is very useful when you want to display names or titles with proper capitalization. The second getter is called initials. This is a very useful extension that extracts the initials from a full name. First, we call split with a space character. This splits the string into a list of words. For example, if the input name is John Doe, it becomes a list of two elements, John and Doe. Next, I call the map function on this list. The map function transforms each element of the list. From each element E, I check if it is empty or not. If it is not empty, I take the first character using E of the 0th index. If it is empty, I return an empty string. So after the map operation, John becomes a capital J and Doe becomes a capital D of the word Doe. Next, I call the join with no separator. This combines all the characters into a single string. So capital J and capital D becomes concatenated JD. Finally, I call to uppercase to ensure all initials are in uppercase. So if you have a name like John Doe, the initial getter returns the capital J and capital D. This is very useful for displaying avatar placeholders or just representation of names in shortened form. The third getter is called masked. This is used to hide sensitive information like email address and phone numbers. The implementation uses a ternary operator. First, I check if the string length is greater than 4. If yes, I show the first 4 characters followed by asterisks. If no, I return the string as it is. The substring 0 to 4 method extracts the first 4 characters from the string. Then I concatenate 4 asterisks to hide the rest. This way you can show a hint of the email without revealing the complete address. This is commonly used in user interfaces where you want to display partial information for privacy reasons. Next, we move on to integer extensions. This extension adds two useful getters to the integer number. Working with numbers often requires formatting them in specific ways. Instead of writing formatting logic everywhere in your code, you can create extensions that handle this for you. The first getter is called ordinal. This converts a number into ordinal form. Ordinal numbers are numbers that indicate positions like first, second, third, fourth, and so on. The implementation is a bit tricky because English ordinal numbers have some special cases. First, I check if the number is between 11 and 13 inclusive. Because 11, 12, and 13 are special cases, they end up with th instead of st, nd, or rd. So 11 is 11th, not 11st. If the number is not in the special range, I use a switch statement on the last digit of the number. I get the last digit using the mod 10 operator, which is the modular operator. It gives the remainder when divided by 10. If the last digit is 1, I return the number followed by st, so 1 becomes first. If it is 2, I return the number followed by nd, so 2 becomes second. If the last digit is third, I return the number followed by rd, so 3 becomes third. For all the other digits, I return the number followed by th, so 4 becomes fourth, and so on. The second getter is called as user ID. This formats an integer as a user ID with a prefix and leaving zeros. The implementation uses string interpolation. The start is with a prefix USR and then concatenate the number. But before concatenating, I call toSubstring to convert the integer to a string. Then I call padLeft. This adds padding to the left side of the string. The first parameter 4 is the total length I want. The second parameter 0 is the character to use for padding. So if the number is 1, toString gives 1 as a string. The pad left adds 3 zeros to the left, giving 0001. Combined with the prefix, the final result becomes USR-0001. This is very useful if you want to display user IDs or any kind of reference numbers in a consistent form. Finally, let me explain the datetime extension. On the datetime class, the datetime operators are very common in applications, and having extensions make them easier to use. I have created two getters, formatted and time ago. The formatted getter is very simple. It returns the date in day, month, year format. I use string interpolation with day, month, and year properties of date type. These properties give you numeric values directly. So if you have a date, say January 10th, 2026, the formatted getter will return 10/1/2026. You can modify this format based on your requirements. Some regions prefer month, day, year format, which can be easily managed. Next, we go on to the time ago getter. It calculates how long ago a date was and returns a human readable string. First, I calculate the difference between the current time and the given date using the date time dot now dot difference of this. This gives me a duration object. Then I check the difference in different units, starting from the largest. If the difference is in days and it is greater than 0, I return the number of days followed by d ago. So if something happened 2 days ago, it will return 2d ago. If the difference is in hours and if it is greater than 0, I return the hours followed by h ago. So if something happened 3 hours ago, I return 3h ago. If the difference is in minutes and it is greater than 0, I return minutes followed by m ago. So if something happened 45 minutes ago, I return 45m ago. If none of these conditions are met, it means that the event has happened very recently, so I return just now. This kind of relative time display is very common in social media applications and messaging applications where you want to see when somebody was active or when a particular message was received.
That is all with the presentation.